Hi guys, today we're going to talk about range, interquartile range, and distribution of data on a box plot. We already know range. We'll talk about what interquartile range is, and the way we find it is very similar to finding the range actually, and distribution of data. Now it's going to be a little different from when we talked about distribution on a dot plot or histogram because we can't see as easily how the data is, where it's concentrated. Is there a uniform distribution? Is it going to be more of a symmetrical distribution, or is it going to be skewed in one direction or the other? We can see that, but it's going to be a little different. The I can statement we're working on is I can find and interpret measures of variation. So the first question you might be asking is, what is a measure of variation? Well, in sixth grade, we're going to learn two different measures of variation, the range and interquartile range. Now, you already know the range. The range is the spread of the data. It is the difference between the highest and lowest data item. I'm going to take the biggest number, I'm going to subtract the smallest number, I get my range. Now, that range might sometimes be a little skewed if I have an outlier. It's going to make it seem really, really big, and you're going to think the data is really spread, but really it might not be. Most of the data might fall into one little spread, and because of that outlier that's really, really big or really, really small, it's going to make it look like the data is way wider than it actually really probably is. And that's where the interquartile range comes in. The interquartile range looks at just the spread of the middle 50% of the data. So this is not going to be affected by outliers. We're just going to be looking at the average middle section of the data. What is that spread? And when we have a box plot, it's very easy to find because the middle 50% is going to be the difference between the third and first quartile. So it's excluding any possibility of those really long whiskers. So let's look at a box plot and find the measures of variation from there. So let's look at this problem. Students were tested on the novel The Giver in November. Their scores were displayed in a box and whisker plot. And here is that box and whisker plot. So the first question we need to ask ourselves when we look at a box plot is, what attribute is being measured? What is it that we are looking at in this box plot? What data is being represented by these numbers? And the answer here is test scores, because all of these numbers are the different students' test scores, or a general description of these students' test scores. What is the median of the data? Well, the median, as we know, is that center line of our box plot. So in this case, it is 81.5 or 81.5. Now, if I want to find the range of the data on the box plot, I'm going to take my highest value, which is 100, and my lowest value, which is 63, and subtract them. And I know that's my highest and lowest because that's how I find my upper and lower extreme when I make a box plot. So I would take 100 minus 63, and my range is 37. Now, the interquartile range, as we said, is quartile 1 and quartile 3, their difference. So if I wanted to find the interquartile range on this box plot, I would take 92 and subtract 73, and I would get 19. So what does this have to do with percents, you might be wondering? Well, if I divide something in half, I know the first half would be 50%, the second would be 50% as well. When I divide data into fourths, each fourth represents 25% of the data. So let's explore this idea a little further. If I'm looking, same data, haven't changed the graph. If I'm looking at this data, I might want to find out what percentage of the data falls in different parts of my graph. Well, if each part is worth 25% of my data, because I've evenly divided my data into 4 equal parts, the interquartile range would take into account this 25% of the data plus this 25% of the data. So altogether, that would be 50%. Now in this problem, I want to know what percentage of the students scored above 73. So I look at 73 and everyone above. So I'm looking at this whole portion of my graph. Well, I've got my entire box, so 25%, 25%, and my fourth quartile, which is also 25%. So altogether, the percentage of students that scored above 73 is 25 plus 25 plus 25, or 75% of my data. Now, if I want to look at 25% of the students, the lowest 25% of the students. So 25% of the students scored below what score? So looking here, if this is also 25%, this is my lowest 25%. And let me erase here so you can see these numbers a little better. So if this is my lowest 25%, what value did they score below? Well, looking at my first quartile, they would score below 73. Now it's your turn. Pause the video. You can go back and rewatch the first part of this video, but pause the video and try to answer these questions for problem number 1. We're looking at a different problem. A fast food restaurant kept count of how many chicken nuggets kids' meals were sold every day for 2 weeks. The data was displayed in a box and whisker plot. So, pause the video, answer these questions, and press play. We'll check your work. All right, let's check your work. What attribute is being measured? What do these numbers represent? The number of chicken nugget meals sold each day. What is the median? So we know from a box and whisker plot, the median is displayed by this line down the center of the box. So the median is 26. The range of the data would take into account our highest and lowest item, which we find on a box and whisker plot because we plot those as our extremes. So 34 minus 15 is 19. And then the interquartile range is the range of our box. Q3 minus Q1. 30 minus 20 is 10. Now try this one. Remember, each quartile represents 25% of our data. Pause the video, answer, 25%. Answer these 2 questions, then press play. We'll check your work. Okay, what percentage of days did they sell more than 30 meals? Well, here's 30 meals. What percentage is more than that? 25%. And 50% of the days they sold less than what number of meals? Well, we need to find 50%, the lower 50%, which is here, 25 plus 25. So the answer would be 26. Now let's talk about one more thing. What if I have more than one box plot that I'm comparing on a graph? I'm going to look at these and I'm going to look at their concentrations and see how far or spread or squished together the graph is. So looking at this graph, I have 3 different professions: nuclear engineers, police officers, and musicians. And I'm looking at their annual income. So the first question says, which profession has the highest annual income? Well, looking at this graph, I can say that nuclear engineers have the highest annual income because its box plot is furthest to the right. So just a quick visual, I'm going to say, well, this guy's been moved more to the right overall than the others. See, musicians are more spread out. So they've got some really low values and some really high values. So it's less easy to determine how much you would make annually if you were a musician. More importantly, the lowest value for nuclear engineers is bigger than 75% of the police officers, and it's bigger than 50% of the musicians. So the least amount that a nuclear engineer can make is more than half of both more than what half of people in both of the other professions would make. Which profession has the most concentrated annual income? Well, concentrated means most squished together. Which profession can I look at and say, I'm going to make between the smallest range? And the answer here would be police officers. They have the most concentrated annual income because it has the shortest graph, which also means that it has the smallest range. We can also look at IQR, but in this case, we're really going to be looking at the range more specifically. There's probably not an outlier with the officers. Does any profession appear to have an outlier here? Well, yes. The musicians appear to possibly have a larger outlier, so this upper extreme, because the fourth quartile is very long compared to the rest of the graph, although you might be able to argue that Q3 is the same length, so there's no outlier. Either answer would be okay. It's more in your description. You know, fourth quartile is very long compared to the rest, or it's about the same, has about the same range as the third quartile. So now it's your turn. Pause the video and answer these 3 questions. Okay, let's check your work. Overall, looking at test scores from periods 1 and 2, which class scored better on the test? Well, overall, I would say second period has the highest average test score because it's 75% of the data right here. Its upper 75% of the data is higher than 50% of period 1's data. Which class has the most concentrated test scores? Well, we would say second period has the most concentrated test scores because its graph is shorter than first period's, and also it has a smaller range. Again, if there were outliers, you might want to argue the IQR is also smaller, but overall, we generally look at the range. And the final question, does any class appear to have an outlier and explain? I would say yes. Both classes appear to actually have an outlier because the first quartile on each of them is longer than the others. Period 1, you could probably argue a little stronger, has an outlier because it has that really low number, but look, 75% of the students scored 75% or higher, and you've got this one student who, it could be, you know, a bunch of the other students scored right around here in this quartile, and one scored at 60%. We are done with this video now. You can go back and watch any part as many times as you need to, but don't forget to WSQ in your notes. I look forward to our discussion.